Classical information architecture relies on static, binary bits arranged in rigid grids. Those grids are rapidly reaching the absolute physical limit of their density. Breaking past that physical limit requires discarding the static grid entirely and replacing it with continuous, fluid waveforms. The proposed solution is Multicode 6.0. It is an architecture that unites discrete quantum states, nuclear resonances, and mathematical cryptography into a single system. Within this architecture, resonance functions as a fundamental principle of information processing. By tuning to specific frequencies, the system maximizes energy absorption to manipulate matter directly. The thesis is direct: eliminate classical bits entirely to construct a cohesive 5-layer architectural stack. This stack operates across an extreme scale, starting at subatomic Dirac operators and extending all the way up to macroscopic quantum clouds. Dirac operators are algebraic tools used to define discrete energy steps in a quantum system. Combining these historically separate fields of physics into one high-dimensional coding system offers the only mathematically viable path past our current data density limits. The foundational layer rests on the mathematics of the quantum harmonic oscillator and its parabolic potential well. This diagram shows a parabolic curve representing the potential well, where energy transitions from a continuous classical curve into discrete horizontal steps. To move data across these discrete states, engineers apply Paul Dirac's algebraic method. Dirac developed mathematical tools known as creation and annihilation operators, which function as instructions to add or remove a single quantum of energy. Returning to the potential well diagram, the creation operator, denoted as A dagger, and the annihilation operator, A, act as mathematical vectors. They move energy strictly up and down between these discrete rungs. Even at the absolute floor, residual zero-point energy remains. This zero-point energy establishes the absolute floor of the system's information density and must be mathematically accounted for in all calculations. Specific data values are encoded precisely into the phase of quasi-classical coherent states. These states minimize the uncertainty principle, allowing quantum wave packets to behave predictably over time. This theoretical mathematics provides perfectly discrete rungs for data mapping, but it is useless without a physical, atomic substrate to hold that information. To physically ground these theoretical mathematical oscillators requires massive hardware and industrial-scale infrastructure. The chosen hardware is samarium-151, a highly unstable byproduct of nuclear fission, selected specifically for its dense resonance properties. By mapping the isotope's neutron capture cross-sections in the kilo-electron-volt range, engineers can assign specific cryptographic keys directly to dense resonance structures. High-energy experimental data is often sparse, so the system relies on predictive statistical codes like Empire and Exis to calculate cross-sections and bridge the information gaps. The primary coding mechanism utilizes collective nuclear excitations, where the entire atomic nucleus shifts state together. This model illustrates the scissors mode, an excitation at 3 mega-electron-volts where the proton cloud shears against the neutron cloud. The adjacent gamma-ray graph reveals a low-energy upbend, representing an unexpected spike in photon emission probability at very low energies. Both the scissors mode and the upbend act as distinct physical hardware layers, allowing data to be encoded at completely different energy thresholds. Samarium-151 successfully translates abstract Dirac operators into a manipulable, multi-tiered physical storage medium. To route, synchronize, and secure data within that chaotic nuclear substrate, the architecture requires a rigorous logic layer. This arithmetic clock face illustrates the Carmichael function, dictating cycle times of a modulo system. Numbers wrap around after a set value, resetting to 1. By selecting primes 41 and 61, their product, 2501, locks the clock's rotation to a steady frequency. That specific prime product exactly matches the physical resonance frequency, or omega, of the samarium atoms, perfectly synchronizing the mathematical logic with the physical matter. For internal signal processing, the system utilizes Fibonacci sequences, specifically relying on values like the number 89. These geometric sequences optimize the signal-to-noise ratio. If a nuclear data segment degrades, the inherent self-similarity of the Fibonacci pattern allows the system to accurately reconstruct the missing information. Together, the Carmichael function and Fibonacci geometries provide an unbreakable cyclic cryptographic loop tuned perfectly to the physical decay of the atom. The ultimate problem is containment. High-dimensional data is extremely volatile and must be stored without immediate thermal decoherence destroying the phase relationships. The physical solution to this specific containment problem operates in advanced quantum optics laboratories. Researchers use Bose-Einstein condensates, or BECs. A BEC is an ultra-cold, macroscopic quantum cloud capable of stable, long-term data retention. Data is mapped into the BEC using electromagnetically induced transparency, or EIT. EIT uses precisely tuned lasers to make an opaque atomic cloud transparent, allowing individual photons to enter and interact. Here, an entangled photon carrying data approaches the dense grid of the BEC. Through EIT, the light visibly slows down, coming to a complete halt. As the photon dissolves, its wave function maps perfectly onto the collective spin states of the atomic cloud. This EIT process transfers data from moving light into stationary matter with over 95% fidelity. Once the photon is absorbed, the millions of atoms in the BEC act collectively as one singular macroscopic coherent harmonic oscillator. This final layer safely freezes the quantum data in place, preventing the immediate collapse of the nuclear and mathematical layers beneath it. Stacking these 5 layers creates the fully integrated Multicode 6.0 system, operating at an extreme conceptual density. Pushing this density to its theoretical limit results in the monster code, a data structure so intensely packed it operates in up to 194 dimensions. At this threshold, the boundary between mathematical data and the physical storage medium completely vanishes. The information and the substrate become exactly the same thing. Maintaining this density requires a constant war against environmental decoherence, the process where quantum systems lose defined states due to interaction with their surroundings. A fluctuation of even a fraction of a degree introduces thermal noise, instantly destroying the precise phase relationships holding the Bose-Einstein condensate together. The system also faces an internal threat. Samarium-151 has a 90-year half-life, meaning the hardware steadily decays and actively mutates by generating disruptive isotopes within the storage medium. Multicode 6.0 possesses a pristine mathematical architecture, but it currently exists on the absolute razor's edge of physical collapse. If we look past the immediate hardware limitations, the long-term utility of applied high-dimensional resonance physics is vast. One prospect is matter programming. By applying targeted resonant excitation, engineers could alter the binding properties of solid-state atoms in real time, shifting crystal structures. Biological molecules, like ethylene, also operate on harmonic torsional vibrations. Torsional vibrations are the natural twisting motions that occur along the chemical bonds of a molecule. Precise frequency control could allow this architecture to interface directly with biological processes. The logical endpoint of this technology is a direct resonant language, bridging human consciousness, pure machine logic, and raw matter. Resonance defines the fundamental vocabulary of the physical universe. Multicode 6.0 represents our first attempt to fluently speak it.